All right, let's dive right into this explainer and uncover the totally fascinating microscopic circuits that physically remember every single thing you do on your devices. Seriously, whenever you use a smartphone, type on a keyboard, or even just wait at a traffic light, you are completely relying on invisible, microscopic memory elements. So today, we are deep explaining flip-flops, which are basically the absolute fundamental building blocks of digital electronics. So here's our roadmap for the deep dive. We'll be hitting 1. The brain's digital memory, 2. Bistable and sequential circuits, 3. Everyday real-world analogies, 4. The critical clock signal, 5. The 4 flip-flop types, and finally, 6. Why VLSI engineers care. Starting off with Section 1, the brain's digital memory. Okay, to start at the absolute micro level, picture this. You're typing the word hello on your laptop. Have you ever wondered how the computer actually knows you already typed the H before you even press the E? I mean, if a digital system didn't have a way to temporarily store every single bit of data, each new keystroke would just instantly erase the previous one. Your computer would literally never be able to complete a simple word, let alone run a complex operating system. Well, the brilliant engineering solution to that exact problem is the flip-flop. By definition, it's a bistable sequential circuit. And sure, it's built using standard logic gates, but it has this really clever twist, a feedback loop. This means the output's electrical voltage is quite literally routed right back to power its own input. This physical loop is basically a magic trick that keeps the circuit alive indefinitely, so it can hold on to its current state long after the original input signal vanishes. Moving right along to Section 2, bistable and sequential circuits. So let's completely deconstruct that kind of intimidating technical definition into something totally logical. First, let's look at the word bistable. The prefix bi simply means two. So this circuit has exactly two stable states. State 1 means the output is a 0, and state 2 means the output is a 1. Now, the absolute beauty of a bistable circuit is that once it enters one of these states, it stubbornly remains there until a new input forces it to change. This persistence, this total refusal to change without permission, is precisely why we call it memory. And that brilliantly illustrates the second part of our definition, sequential circuits. Think of a combinational circuit, like a standard AND gate. It has absolute amnesia. It's just reacting to current inputs, kind of like real-time math. You change the input, the output changes instantly, no memory whatsoever. But a sequential circuit, like our flip-flop, introduces the concept of time into the equation. Its output depends on the present input and its previous history. It literally physically remembers what happened a moment ago. All right, Section 3, everyday real-world analogies. To deeply understand this concept of state retention, let's pull these tiny circuits out of the computer and connect them to the real world, the things we interact with every single day. If an output flips to a 1 and then flops back to a 0, it's exactly like your bedroom light switch. You press it on, you walk away, and even an hour later, that switch remembers its position. It stays on. Or think of a physical notebook. You write on page 1, close it, and when you open it tomorrow, the ink is still there. The notebook is acting as memory. A flip-flop does the exact same thing. It's like storing an electronic drop of water in a bottle for later, or acting like a chair that maintains an occupied or empty state until someone actually stands up. The crucial takeaway here is that while we humans use incredibly complex concepts like yes and no, or true and false, a flip-flop only ever stores exactly one bit, one binary digit. It translates all our rich, nuanced human ideas into the strict, rigid binary language of ones and zeros. And remember, physically speaking, a 1 simply means a high electrical voltage and a 0 means a low voltage. A single flip-flop physically traps exactly one of those high or low voltages inside its circuit. Which brings us to Section 4, the critical clock signal. Now, you might be wondering, if a circuit is holding on to a 1 or a 0, how does it actually know when to update? It can't just change randomly, right? Well, think of a high-pressure classroom exam. Before the exam officially starts, you can think, you can change your mind, your thoughts can fluctuate all over the place. But the exact split second the teacher yells, "Start," you write your final answer down on the paper. After that, the answer stays locked on the paper. It doesn't change until the next instruction. This perfectly describes the clock signal in digital electronics. The data is your thought process, but the active clock edge, that is the teacher yelling, "Start." Because you see, in a really complex digital system, you absolutely cannot have components updating whenever they feel like it. Synchronization is essential. Millions of flip-flops have to update together precisely on a specific clock edge, either the exact moment the clock signal rises or the moment it falls. When that edge hits, the flip-flop locks in its data and outputs its primary value, which engineers call Q. But here's a cool bonus. It also outputs the exact opposite value at the same time, known as Q bar. And getting this inverse output for free is a massive advantage for engineers because it saves them from having to build extra separate NOT gates later on. Oh, and a quick point of clarification here, because you might occasionally hear the term latch thrown around in this context. There's a big difference between latches and flip-flops. A latch is kind of like pushing down on a cushion. It is level sensitive. It reacts and flutters the entire time pressure or an enable signal is being applied. But a flip-flop, that is like a staircase. It's edge-triggered. It only steps up or down at the exact split second the clock signal rises or falls. And that rigid timing makes flip-flops vastly more reliable for highly complex synchronous systems, like the processor in your phone. All right, let's jump to Section 5, the 4 flip-flop types. So let's actually look at the hardware variations because there are 4 main flavors. First up is the SR, or set/reset flip-flop, which is basically the most basic kind. Then there's the JK, an improved version of the SR that cleverly prevents invalid input conditions. Engineers use those a lot in counters. We also have the T or toggle flip-flop, which does exactly what it sounds like. It simply flips its output from 0 to 1 or 1 to 0 every single clock pulse. But the undisputed king of modern integrated circuits is the D flip-flop, where D stands for data. Its simplicity totally prevents ambiguous states, making its behavior incredibly predictable and safe from massive systems. And when you look closely at the logic for the D flip-flop, you can completely see why it's so popular. It's just brilliantly straightforward. When that rising clock edge hits, if the data input is 0, the next output becomes 0. If the data input is 1, the output becomes 1. But check out that bottom scenario. This is where the magic happens. If there is no active clock edge, it literally does not matter what the data input does. The output vigorously holds on to its previous value. And finally, Section 6, why VLSI engineers care. We've spent a lot of time looking at the micromechanics, so let's zoom way out to the massive macro scale of chip design. Where are these things actually used? Well, literally everywhere. Without flip-flops, there are no CPU registers to hold your data. There is no static RAM. Every single digital watch that counts seconds uses flip-flops. Moving data over a wire using shift registers? Flip-flops. Even the traffic light controller at your local intersection completely relies on flip-flops to remember the sequence of green, yellow, and red. Honestly, none of these technologies would exist without them. And we aren't just talking about a few dozen of these in your computer. Every single modern CPU and GPU inside your laptop or smartphone contains literally billions of these tiny memory elements. Billions. Packing that many circuits into a chip the size of your fingernail presents a staggering, awe-inspiring challenge for very large-scale integration, or VLSI engineers. And because there are billions of them, VLSI engineers have to rigorously optimize flip-flops on 4 major fronts. First, timing. They have to define the strict boundaries between stages of processing. Second, performance. The physical speed of your flip-flops literally sets the maximum clock frequency, or gigahertz, of your entire processor. Third, power. Charging and discharging these microscopic capacitors requires physical current flow, which creates thermal friction. Flipping billions of switches generates a massive amount of heat. And finally, area. Making these designs as space-efficient as possible saves incredibly expensive, highly valuable silicon real estate. I absolutely love this quote from the source material we're analyzing today because it anchors all of this dizzying microscopic engineering back into a deeply relatable human concept. It says, if logic gates are the brain that make decisions, then flip-flops are the memory that remember those decisions. We need logic to decide what to do, for sure. But without memory to actually store the result, all that processing power is completely useless. The flip-flop provides that absolute critical permanence. So, as we wrap up this explainer, I'll just leave you with this thought. Think about every pixel, every letter, every video frame that you're looking at right now. It is currently being held in place by billions of tiny electronic notebooks, rapidly flipping and flopping to the precise beat of a digital clock. Next time you power on a device, take just a moment to appreciate the incredible microscopic memory making it all possible. See you in the next one.